Hey, condensed sauce. Noah here, and John. John, what you got there?
Right here, Noah, I got myself a nice traditional lighter. The way that this lighter works is that it uses flint and steel to create a spark, which in turn lights the butane gas, creating a nice, beautiful, and constant flame. But Noah, I gotta ask, how exactly does that work over there? Is it the same way?
Well, this here, John, is a completely different beast. We have a standard issue 11-inch military grade grill lighter right here. There is no such flint and steel inside here to create a spark, nor is there even a battery. This will last conceivably forever. So how does this make a spark and light the flame? Crystals.
Whoa.
Looking at this lighter from a top-down view, you can see I have removed the safety so that when I pull the trigger, the lighter will ignite. Taking a look at the other side, you'll see we have already removed half of the protective casing, and you can see what's really going on. We have four main elements here: the butane tank, the clear wire, two more white wires, and this trigger housing. The clear wire is connected to the butane tank, and it transports the butane up to the tip of the nozzle, where the gas will ultimately be vaporized due to the decrease in pressure. The two white wires lead into this trigger mechanism, and the only logical deduction you can make is that this is the source of the arc of electricity that ignites the butane. But we can clearly see there's no battery. Instead, this is a closed spring mechanism. By pushing the trigger, it simultaneously opens the butane tank with this small switch, and simultaneously loads this springed hammer right here. It makes an audible click. Once the trigger is fully pushed in, the spring is fired and hits a piece of crystalline quartz, which creates a potential difference within the piezoelectric material. Since we have a non-zero potential, a current will flow through the circuit. Even though the circuit is technically open at the nozzle's tip, the potential difference generated will be great enough to arc through the air across the nodes of the tip of the nozzle and ignite the butane gas.
Whoa, that's awesome. To think that electricity is completely generated by simply applying a force to the quartz?
That's right, John. A mechanical force causes a non-zero potential difference to arise throughout the material.
So, what is this property called? I think I heard you say earlier piezoelectricity. Is that it?
It sure is. In fact, piezoelectricity was named after the Greek word for pressure, pieza.
So, who discovered such a cool phenomenon, and how long have we known about it for?
Well, Pierre Curie, husband of Marie Curie, and his brother Jacques Curie were responsible for discovering piezoelectricity and formalizing it in the March of 1880.
How'd they even think to begin looking for such a thing?
Well, other scientists of the time suggested that a possible relationship would arise between pressure and electricity in certain materials.
So, does this mean that this piezoelectricity works for other materials? And better yet, why does it work?
Well, John, let's explain that in a way that Dr. Ochoa would appreciate. Let's dive into the certain property a material needs that allows piezoelectricity to occur in significant scales. We know that not all materials are piezoelectric. Things such as diamond fall into this category. This arises from the crystalline structure of a diamond having a strong symmetric shape. Quartz, on the other hand, lacks mirror symmetry when observed. However, what both of these molecules have in common is that they are electrically neutral and that the average position of positive and negative charges overlaps. When we deform diamond, this relationship is preserved. However, with piezoelectric materials such as quartz, the crystal structure becomes polarized, meaning that a potential difference will inevitably occur.
So, a deformation of such a material will create a dipole, since the average position of charge does not overlap within the cell. As previously stated, a piezoelectric material not experiencing any outside force will maintain this fragile, electrically neutral balance, keeping a net zero potential difference.
Here are some of the examples of piezoelectric materials. Each of these will create a net potential difference within themselves when an outside force is applied.
This is a simulation I made in Desmos, which models the compression of a hexagonally symmetric crystal structure. So it works for quartz. As the ions that compose the crystal structure are pushed in, the net average position of positive and negative charge moves away from one another, thus creating a potential difference.
Gabriel Lippmann was a 19th century mathematician that predicted that the piezoelectric effect could theoretically work in the opposite direction. This is to say that applying a potential difference across the material would result in a deformation of the material. This was experimentally verified by the Curie brothers shortly after Lippmann made this prediction.
In an effort to test Lippmann's hypothesis, the Curie brothers went back to the lab to see if the theory matched experiment. They successfully observed the effect, confirming that Lippmann was indeed right. The effect predicts that if a voltage is applied to the crystalline material, it will experience a deformation via expansion. If the material is cut correctly, then this can allow for precise length elongation about a certain axis. This right here is called an atomic force microscope, often abbreviated as AFM. The device uses the inverse piezoelectric effect indirectly to its benefit. The AFM is very good at determining the height profile of small samples when there's very small variations in height, even so much as so on the order of nanometers. But how can it accomplish such a superhuman feat? Well, as you can see here, the metal chassis inside actually contains a stack of piezoelectric material. We can precisely adjust the voltage that runs through the material and in turn adjust the X, Y, and Z coordinates of the cantilever. While it's not responsible for the actual measurements being made, it brings that cantilever that does take the measurements down to its correct position.
No, I gotta hand it to you. This is honestly such a cool effect. I can't believe I've never even heard about this before.
It really is something to marvel, John, and I think more people ought to know about it. There are so many more uses of piezoelectricity that we didn't even cover, such as watches, sonar detection, and many more.
Well, I'm glad to at least have the basics down. So thanks for sharing all that information, Al. I appreciate it.
No problem. It was my pleasure. After all, this assignment is 15% of my grade.
That's crazy.
Don't worry. I'm sure we'll do fine.
Alba inside. It's Messi! Oh, what a goal!